Bom dia a todos. Hoje é o dia 23 de fevereiro de 2026 e teremos hoje aqui no IMPA, nessa sala, a defesa de tese do aluno Mateus Spezia. Eu gostaria de apresentar os membros da banca. Temos aqui presente o professor Luiz Florit e online a professora Ana Menezes, de Princeton, o professor Ivaldo Nunes, da Universidade Federal do Maranhão, o professor Mikhail Karpukhin, da University College in London. So let me change to English. So Mateus will have 50 minutes to give his presentation. And after that, the members of the committee will ask questions about the presentation, about the thesis. And then everyone will leave the room so that we can deliberate. And then the final announcement will be made. Okay? Okay, so Mateus, you can start, please.
Okay, thanks. Thanks everyone that spent some time to watch my PhD defense. I would thank Lucas for the guidance during these 4 years. You are a great advisor. And I would thank the members of the defense committee for accepting my work. Let's start. My thesis is focused in the relation between minimal surface and spectral geometry. More specifically, I use some immersions given by first eigenfunctions for constructing a free boundary minimal Möbius band in geodesic balls of some sphere. Let's go. This story related minimal surface and spectral problems start with this work of Takarashi in the 60s, and Takarashi proved the following is like more an observation. If we have a closed Riemann manifold of dimension k, and an isometric immersion in some round sphere, then this immersion is minimal if only if the coordinated function here, given by the inner product between the position and the canonical vectors, are eigenfunctions with eigenvalue k of the Laplacian operator. That is, they satisfy the classical Helmholtz equation. Here we have 2 directions. If we have a minimal immersion in some sphere, we know that k is an eigenvalue, but we don't know how specific eigenvalue k is. If it's the first, the second, we know only k is an eigenfunction. And for other hand, if we have eigenfunctions with this eigenvalue k, where k is the dimension, we are able to construct a minimal immersion in some sphere, with the dimension of the sphere is the multiples of this eigenvalue. And I point here, there is a conjecture of Yau when M is embedded and a codimension one, then it's conjectured that this k is the first eigenvalue, but it's still open. In the case of surface with boundary, there is an analogous result by Fraser Schoen observed the following. If we have isometric immersion that send the boundary of our manifold, manifold with boundary, on the boundary of the ambient manifold, then this immersion is minimal and free boundary. Free boundary here means that the boundary meets the boundary of the ambient manifold orthogonally. If the coordination function satisfies the following. They are harmonic, and the normal derivative along the boundary is a multiple of is equal to the function on the boundary of the coordinated functions. This can be interpreted also as a spectral problem. This means that one is a Steklov eigenvalue of the Dirichlet-Neumann operator. I will define briefly what precisely means Steklov eigenvalue. So now let's introduce our ambient manifold. I will interested in my thesis is to free boundary minimal surface in spherical caps, where spherical caps are these geodesic balls of radius r on the round sphere inside the Rn+1. So we try to study minimal surface, and this R varied between 0 and p/2. We are interested in spherical caps in the upper hemisphere of the sphere. Then Lima Menezes observing the analogous conditions for a minimal minimal isometric immersion is be minimal in this setup. They observed that the coordinate function satisfies this equation here. This Helmholtz equation is essentially the work of Takahashi. Is minimal, and the free boundary condition is captured in these two conditions here. This means that minus tangent Fr and cotangent of R are Steklov eigenvalues with frequency 2 of the metric G. Now I will define what means precisely Steklov eigenvalues with frequency. Now it's not necessary an immersion, just a surface with boundary with some metric G. And we take a parameter not in the Dirichlet spectrum of the Laplacian with boundary condition 0. With these conditions, we are able to take one function defined on the boundary and take an extension. This, if the function is smooth, the extension is also smooth, and satisfies the following boundary value problem. They solve the Helmholtz equation, and the trace of this extension is equal to the function on the boundary. Then we define the Dirichlet to Neumann operator, take this function and this extension, take the normal derivative along the boundary. And this operator have very similar properties with the Laplacian operator. In fact, we can prove this is a self-adjoint operator, and they have a discrete spectrum. It starts by a number, and goes to infinity. And this parallel with the Dirichlet spectrum is also captured in the, oh, sorry, here is Steklov, not Dirichlet eigenvalues. Then the Steklov eigenvalue also have a variational characterization. And if we assume here this parameter alpha is less than the first Dirichlet eigenvalue with 0 boundary condition, then the variational characterization is easy. We take the infimum of this Haley quotient along the functions in the sublevel space of sigma. If you will not assume this condition, we need to be more careful with this variational characterization. We need to take the function satisfies the previous equation. But when we impose this condition, so the variational characterization is more easy, and the second eigenvalue is given by the infimum of this Haley quotient, but with the restriction that the test functions should be orthogonal to the first one. And there exists another interesting relation between minimal surface and spectral geometry. Some metrics are critical. Some isometric immersions furnish examples for a natural function defined on space of the Riemann matrices. For example, if we consider a closed surface without boundary, and you take this functional here, you take a metric and take the first normalized Laplace eigenvalue, with the first eigenvalue multiplies by the area of the surface. Then was observed the following: as a series of many works, start with Hersch in the 16th, and the sub of this functional is finite and depends only on of topological constant. So we have a hope that we can find a matrix that maximizes this functional. And Nadrashvili observed that maximal metrics, if there exist, are induced by branched minimal immersion in some Euclidean sphere, and this immersion is given by first eigenfunctions. So the existence of maximal metrics of this functional is a very long story, and the final proof is very recently is the works of Petrides and Karpukhin, Kurzner, Stern, McGrath, gives the positive answer in the case of closed surface. And only few examples of maximal metrics are known. They're only known in the case of sphere, RP2, torus, Klein bottom, and genus 2 surface. So finding a maximal metric for this functional in general is a very hard question, and the work starts in the 60s, and still there works in this direction today. So in general, it's a difficult question. And in the case of free boundary, Fraser and Schoen observed the same for the first normalized Steklov eigenvalue with frequency 0. The sub of this functional is also finite and dependent only on topological constants, depend of the genus in the number of boundary components. And also extremal metrics arise from free boundary minimal immersions in some Euclidean ball, and this immersion is given by first eigenfunctions. And in the case of spherical caps, we have this result of Lima Menezes. They consider the space of matrices on a surface with boundary, but with this restriction on the first Dirichlet eigenvalue because the variational characterization, and consider this functional here depends on the first and the second Steklov eigenvalues with frequency 2, and they observe also this functional is bounded by a topological constant, and extremal metrics or maximal metrics, if there exist, arise from immersions of first eigenfunction with Steklov by first eigenfunctions with Steklov eigenvalue 2 with frequency 2. And so there, at the moment, there is no a theory that asserts there exists maximal metrics for this functional, but I wrote with these recent techniques, they can prove their existence. So if we produce some metrics given by immersions given by first eigenfunction, we produce natural candidates to be the maximum of this functional. So is there our hope? We try. There is, in the case of surface with boundary, the easiest topology is the disk and the annulus. There is maximal. There is some immersion no, and the second and the easiest topology in the non-orientable case is the case of Möbius band. So we try to construct such Möbius band, and this Möbius band provide a candidate to be the maximum of this functional if we are able to prove that there exists this maximum, the maximal matrix. So what mean here immersion by first eigenfunction? Because here we are committing some abuse of notation because we have two eigenvalues. We have eigenvalues minus tangent of R and cotangent of R. And then we say this immersion is given by first eigenfunction is the height function. It is the coordinate function with respect to the coordinate to the vector is 0. The height function is an eigenfunction, and the other ones are second eigenfunctions. Now our goal, I tell you, is construct a free boundary minimum Möbius band in these spherical caps arise first Steklov eigenfunctions. And we prove that such Möbius band, if there exists, are intrinsically Hora symmetric. The K gradient for do this is have an index estimated. And finally, with this symmetry, with this rotational symmetry, you are able to construct such examples of free boundary minimal Möbius band given by first Steklov eigenfunctions. More precisely, our results are the following. First, for R between 0 and pi over 2, we have a Möbius band. Then an immersion in some spherical cap, free boundary immersed from first Steklov eigenfunction. Then this Möbius band is intrinsically rotationally symmetric, and the dimension of these spherical caps is 4 in B4. The second theorem asserts there exists such Möbius band for each R between 0 and P over 2. We are able to construct such Möbius band, and moreover, we can compute the Morse index with this Möbius band is 5. And theorem C give a bond on the Morse index if we have a compact free boundary minimal immersion not contained in the hyperplane passed through the origin, then the Morse index is at least n+1, where n is the dimension of the ambient manifold. Now, we start with the theorem C, the Morse index estimated. The Morse index consists in the maximal dimension of a subspace of the normal bundle, where the deformations of the surface of the area of the deformation with this normal velocity, is negative defined, the second variation of area. And this is encoded in this quadratic form. We can proceed by integration by parts. And here, V and W are section in the normal bundle, and L is the Jacobi operator. So for get an lower bound on the Morse index, we need to produce some normal test sections. So it is what we do for prove this theorem C. We construct these normal test sections, and the idea is the following. We take a vector y in N, and we define this vector here. Phi y is the coordinate function with this vector y. Phi 0 is the coordinate function with respect to the vector is 0. And this vector here, partial y and partial 0, is the tangent projection of this vector field, this vector y, and is 0 in the tangent space of the sphere. And we take the normal part along the sigma. We project on the sphere, and after that we project on the normal bundle of the immersion. So this gives a vector field here, and I start thinking the most natural candidates to be this vector field is the conformal vector field. I try use the conformal vector field. I compute the conformal vector field of these geodesic balls, and try use this vector field as test section in the index form. But when I do this computation, I get a problematic boundary term that I can determine the sign on. It's an integral along the boundary with if I can determine what the sign is precisely. So I put this constant dependent of R and I observe that I can choose this constant for this problematic term on the boundary disappear. And this is a n-dimensional space of normal sections. And when I put the condition that this y is orthogonal to the first coordinate vector, and I observe that I also can take the direct sum with the space generated by the projection of the vector, the first coordinate vector, and get a n+1 dimensional vector space of on the normal section. And why compute when this immersion not line in the hyperplane pass through the origin, then I can compute the dimension of this space, and this is n+1. For each vector in this space, I compute the index formula, and it's given by this expression that is negative unless this vector is 0. So this gives this bound on the Morse index. And now, theorem A. First imposed by symmetries on the Möbius band, the identification of the Möbius band, we get a upper bound to the dimension of this immersion if it is by first eigenfunction, use the Cohen-Nodal theorem estimated. And by work of Carlos, I know this can be 3, then this dimension is 4. And now we prove such, if we have such immersion by first eigenfunction, then is rotationally symmetric. We have the following. We know a Möbius band is conformally equivalent to the cylinder with the correct identifications. Here, sin r minus SR. And then on metric on the Möbius band is conformally equivalent to the cylinder with the correct identification. There exists a conformal factor Rho depend on the angular coordinated and the radial coordinated. That's the metric is conform to the flat metric. And we say this metric is intrinsically rotationally symmetric if the radial coordinate, the conformal factor not depend on the radial coordinate. It can translate to the derivative with respect to the partial derivative with respect to if the angular coordinate is 0. So how we prove this? Let's see how the proof of this theorem follows. First, we observe we have this quadratic form. We start with the quadratic form as relates to the first variation of the area, but there is another quadratic form associated to the second variation of energy. And when we compute on vectors on the tangent bundle, on the pullback bundle, and use the coordinates of these vector fields is given by these functions, this quadratic form can be written as following. So this quadratic form is very similar to the Rayleigh constants that we use for test Steklov eigenfunctions. So there is a relation with this quadratic form with test functions for the Steklov eigenfunctions. So what we do we have the immersion, and we try use the test function of this vector field defined by the derivative with the respect to the angular coordinate of the coordinate functions of our immersion, and try use this as test functions to the eigenvalue cotangent of R. We know this is the second eigenfunction because we are assuming that our immersion is given by first eigenfunction, so this cotangent of R is precisely the second eigenfunction. So first, we assume that we can use these functions as test functions. So when we assume first they can be used as test functions. So this integral along the boundary is 0. Using this, we try to prove the theorem, prove that the derivative of the conformal factor is 0. So what we do, first we observe that the first coordinate function along the boundary is 0 by construction. We are assuming by construction, by the free boundary condition. Then what we have, and as the first Dirichlet eigenvalue is greater than 2, we have the following. This is greater than 0, and the seconds, the others can be used as test functions to the eigenvalue cotangent of R. And between 1 and n can be used as test function for sigma 1 equal a cotangent of R. So the Haley quotient satisfies the following. Oh, we call this one. This is greater than 0. Then sum this and this, 1 and 2, for I bit sum 1 and 2. What you get? You get Q of this vector field with this vector field is greater than 0. But we prove a lemma that asserts this vector is in the nullity of this quadratic form. So is also equal to 0. Here we use the form of this quadratic form, is only sum. Then we get the equality in 1 and 2. So using, for example, the equality in 2, then we have equality in 2, then for I between all right, then these functions are eigenfunctions with eigenvalue cotangent of R, then they satisfy the Helmholtz equation. So they now we can change the order of, so this is equal to this minus, here the Laplacian is as 1 over rho the Laplacian of the round metric, so this is minus the 1 over rho Laplace of the round metric of this function. This is equal to 0, but this is 0. You already know these functions are satisfies the equation by the minimal condition. And this function is for, there is I that this is never 0. Give a point P, there is a less one I, this is different from 0. Then what you get is this partial derivative here is 0. This implies that the derivative of rho with respect to the angular coordinate is 0. So we get this function not dependent on the angular coordinates. So we need to prove this, that this condition here is it's true. It's not an arbitrary condition. It's in fact true. So we proceed as following. We can prove that there exists a subspace of dimension at least n on this spatial C that we construct in the proof of the index estimated, where the quadratic forms coincide. Basically, we take a vector in this space C1, a subspace of this space when the index is negative, and produce a tangent deformation in order that this new vector field is conformal. And for this conformal vector field, it's true that this quadratic form coincide. And here the V is normal, so this part V is unnecessary. And so then we define the following functional. We take a functional to C1 is normal section times the space generated by this vector field here is a tangent, and this is a normal section, and we go to Rn plus 1. We take a vector V and a C here and take the integral along the boundary, this vector yv plus c times this vector. And observe the following. We define this function, the coordinate function of this vector field, fy. First, observe that f0 restrict to the boundary is 0 by is followed by the free boundary condition and the construction of this vector yv. And the other, so these in fact take values in Rn, not in Rn plus 1. These are n-dimensional space, is a one-dimensional space. Then there is at least one element on the kernel. Then exists V in C1 normal and C in R, such that this integral is 0. Now we try proof that this vector V is 0. So we can, as these elements are no both 0, so C is different from 0, and we get in the first step. And now we can use again these functions f and fy as test functions. So by proceeding analog to the previous case, what we get? We get the Q compute in this vector yv plus cv is greater than 0, was as test functions. But for other hand, we know this vector here is in the nullity of this quadratic form. Then this is equal to Q yv, but yv is equal to the quadratic form associated to the second variation of the area, v. And by the index estimated, we know this is less than 0, and the equality flows when this v is 0. So here we have the equality. Then v is 0. By construction, this yv is also 0. And then the c is different from 0. And we get on the previous case. So this is, unless the idea of the proof of this theorem A, of course, the proof of the most difficult part of the proof consists in proof these two lemmas. And now the theorem B. Using these symmetries, now we know if we will have immersion by first Steklov eigenfunction, then by theorem, the previous theorem, we know this immersion is rotationally symmetric. So we can reduce the equations to be minimal, the partial differential equations to a system. First, as I say, by theorem, by the theorem of Carlos, and use this coordinate domain, we get this, the dimension is 4. And after that, using the symmetry and do a separation of variables, a little Fourier analysis, we can reduce the system of partial differential equation to a system of differential equation. Ordinary differential equation is more easy to deal with this. And essentially, we have 3 differential equations, and this equation are parameterized by a parameter A, and this parameter A essentially is the 1 minus A squared, essentially is the maximal height detected or Möbius band assumed with respect to the orthogonal plane. And So essentially, we need, and we have also the boundary conditions here is translated to this condition. The condition we tell the Möbius band is in this spherical cap, and the condition B is the normal derivative condition. And also we have this symmetries of the identification of the Möbius band gives some information about the parity of this function satisfied. The height function must be even, and the other have this odd and other is even functions. So essentially, the next proposition I said, if we find a parameter given r between 0 and pi over 2, if you find a parameter a between 0 and 1, and a height of the, I raised it here, but you find the height of the Möbius band when the solutions of this differential equation here have this following properties, with this expression here give for us a free boundary minimal isometric merge of a Möbius band, of such Möbius band. So the difficulty is find this parameter A and parameter SR. Is the difficult, and in fact, in the previous slide we have 3 equations, but we have this condition. X is given by this, the condition to be in the sphere give a completed, so you can reduce the system for 2 equations. And the main difficulty is now how find this parameter A for the solution have these appropriated conditions. And the proof of theorem B consists in this lemma that assert for given r between 0 and p over 2, we can find such A and such SR. It's such that the solution have the solution of the differential equation has the required properties. And the proof is followed by the following. Also, Spezia, Giacomini, and Hazard, when they are studied the Klein bottom, immersed by first eigenfunction of the Laplace operator, already studied this system of equation, and they found these 2 first integrals. These first integrals means that there are expressions on the phase space, and the solutions of the orbits of the solution of these differential equation lie in this intersection of these 2 algebraic varieties in the phase space of the differential equation. And with these 2 first integral, we can reduce these differential conditions here using, moreover, they find another special sign when also the orbit lies. And using this, we can reduce this differential condition to an algebraic condition about this parameter A. And these algebraic conditions, we know only guarantee that the roots of this equation satisfies the condition 1 minus A squared greater than cosine of R for the solution B in the correct side of the spherical cap. And in fact, we can find the solution. Oh, sorry. In fact, we can find there are 2 roots of this differential equation, and in fact, we can find at least 1 root with this property. And moreover, observe when R goes to 0, this root goes to 0, and when R goes to pi over 2, this root goes to square of 3 over 8. And this 3 over 8 is very special because this A equal 3 over 8 corresponds to the A that we found by the work of Spezia, Giacomini, and Hazard in the construction of the Klein bottom. So when we take the limits, our free boundary Möbius band correspond in fact with the half of the Klein bottom in the hemisphere. So that's it. Thanks, everyone. And questions? Thanks.
Okay, thank you very much, Mateus, for the presentation. So we have a tradition here. We should begin with the member of the committee who is further away from IMPA. And I think that is Misha. So Misha, please.
Right. So very, very nice talk, very nice results. Thank you for your presentation. Can you speculate or say something about the uniqueness of this Möbius band?
Yeah, is this the part of that I not can able to conclude, because when I do the analysis of this differential equation, I find this a between 0 and square of 3 over 8. So for this a, by the uniqueness of solution of differential equation, by this a, there is a uniqueness solution. But for a greater than these values and 1, I'd not be able to conclude that there exists a solution, but with my techniques, I'd not be able to conclude if some a greater than these values give a free boundary minimal Möbius band in some spherical cap. I have a hope that they can be found because some numerical simulations that I do, and I observed that for a greater than this value, in general, these Möbius bands tend to be free boundary with respect to geodesic balls with R greater than pi over 2R, are free boundary in the lower hemisphere. But I not find a solution. It's a frustrating part of my work. I want to be, and my objective is give such uniqueness for classifying. But I hope that is possible. But this ODE part is not my specialty, and I don't know how proceed and do this.
So numerically, you're saying?
Yeah, numerically,
it seems like they're unique.
Yeah, and for this, for R close to 0, there is a uniqueness because for a small, the Möbius band such start in this upper part, and for B in the upper part, this 1 over 1 minus a squared should be small. So for the R close to 0, there is the uniqueness. But for R close to the equator, I don't know. But in the equator also there is a uniqueness because the work of El-Sophie, Hazard, and Giacomini found a uniqueness claim bottom. If I have a such Möbius band, I can do a reflection and get another claim bottom. So there is a uniqueness also. Then there is a missing R between pi over 2 and some small r, or I don't have the uniqueness with these methods.
Okay, so another question, Misha? Or?
Not yet. Maybe.
Not yet. Maybe
I
later.
get inspired by other.
Okay. So let's go now to Princeton. Anna.
Okay, so first let me thank Lucas for inviting me to participate in this committee. It was a pleasure to read Mateus' thesis. It's in a topic that I'm really interested in, so it was very nice to see the results that he got. I think the thesis was very well written. I could only find a couple of typos that I'll mention to Mateus later. It's very, very few. For the oral presentation, I think Mateus did a very good job in finding a good balance between technical details and just the general idea. That was nice. For the results themselves, I really like them. I think they contribute a lot for the understanding of free boundary minimum immersions in spherical caps. And well, the questions that I have, I could ask what you know about the embeddedness of these examples that you found. Can you say something?
I think they are embedded because the first coordinate function not depend on the on the parameter, the angular parameter, and so in general they are embedded.
So if you if you think they are, I think it would be nice that you include that information in the thesis. I think would be nice. People will keep asking you that question.
Yeah.
And well, the natural next question is: did you try to think about these examples in the next space? So you found in spherical caps. Did you try to find in the hyperbolic caps as well?
Yeah, as a natural question is in fact a future project that I have, and in general the first two parts are basically the same because of the work of Medvedev. I know that there is an analog theory, and so they will be rotational symmetric, and so I need to analyze the differential equation. The differential equation change one sign essentially. It's the same differential equation, but with a sign change, and now I need be the analysis of these differential equations for construct the examples. But there is no a theory like in the previous case, so I don't try do this, but I pretend explore this in a future.
That's nice. Mm-hmm. That's nice. Thank you, Mateus. I'll let my other colleagues ask some questions as well.
Okay, thank you very much, Ana. So, Ivaldo?
Okay. First of all, thank you for the invitation, Lucas and Mateus. It's a great pleasure to be here in this committee. Congratulations, Mateus, for your talk. It was very clear. So about the text, I made some observations and comments in the PDF file, and after this meeting, I will send to you, Mateus.
Okay.
About the question, I have some questions about your Morse index estimate you did in your work, because I know that you made a little improvement with respect to the first version.
Yeah.
And the first version you had to prove that the Morse index was greater than or equal to n, and then after the second version you improved this estimate for n plus 1. Do you know if your technique can be used to improve the estimate of the Fraser and Schoen's estimate for free boundary submanifold in the unity ball? Because in the work the estimate is greater than or equal to n.
Okay, but in their work, I commit the same mistake, because in their work you also find the estimate n plus 1, in fact, with addition this direction by the position vector. I think in the work of Fraser and they proved this index estimate with the vector in Rn, and also they need the position vector, the normal projection on the position vector. So I think in the work of Fraser you also get this n plus 1 index estimated. In fact, I realized this because in the proof, in my previous verse, in the proof of theorem A, in fact, I use this n plus 1 dimensional, but I don't write. So I talked with Ivan, my colleague, about this result. I found better to write in the previous section, in this section, index estimate this n plus 1 estimate, because in fact this is already contained in my work, but is not explicitly. So I decided to make this explicit. And in the previous version, I found this constant CR in a artisanal way. And when I rewrite, I I realized that I can extract this constant C of R as root of an polynomial that vanish the term on the boundary. So rewrite the proof. I found this constant better in the previous version. Essentially, I write and I realized that this constant eliminates this problematic term. And after that, rereading the work, I realized that it can be this more clean, more.
Okay. Another question. Maybe it's a very basic question. In theorem C,
Okay.
you did the computation for R not equal to pi over 2, and what happens with if R is equal to R over 2, pi over 2
Pi over
in the MC? It's the same estimate. Is it a basic question?
Yeah, I avoid write this because for pi over 2, there are no more, the coordinate function are no more Steklov eigenfunctions with frequency 2 because the height function is zero on the boundary. So there is not a precise definition, so I avoid this for keep R greater than pi over 2 for this coordinate function B, Steklov eigenfunctions. And I observe in the limit case, when R goes to pi over 2, such Möbius band that I construct converge to the half of this Klein bottle. This is the observation. But it's not correct to say this Klein bottle is immersion by first eigenfunctions in the sense that I wrote because the zero condition of this height function on the boundary. Then this is not a Steklov eigenfunction here. The analytic problem not makes sense in this case.
But I think he asked about the index.
The index.
The index.
The index is the same. I think the index the same estimate of the index is also true. Is more easy in the case of pi over 2 in the half sphere. I can use just the conformal vector fields and the conformal group forget this index, and I get this lower bound estimation. I know the index is greater than pi over greater than 5, but the upper index I not can use the theory because for estimate by index by above, I use the index is less than the spectral index plus the dimension of the moduli space of the conformal structure of the surface. Forget the upper bound. And I don't have this, what means the spectral index in this case. So I only have the lower bound. The upper bound, I need to find other proof for this. Maybe using the index of the Klein bottle, I think that is computed, I can give the upper boundary for the index.
Okay, just one more question. When you consider free boundary submanifold in a convex geodesic ball, you know that minus tangent is the first Steklov eigenvalue, but you don't know if cotangent of R is the second one. Do you know if it's possible to obtain some Choi-Wang's inequality or Fraser inequality for this second Steklov eigenvalue? Something like cotangent over 2, cotangent of R over 2.
I think it's a good question.
Have you tried to do this?
I not try to do it, but I pretended do this. I make some. I think it's direct for the work of Fraser Schoen. They adapted directly in this case. Is the same Rayleigh formula, so I think it's a direct computation. But I don't do this. But okay. I think that is possible be true.
Okay, thank you, Mateus. Congratulations.
Thanks.
Okay, thank you, Ivaldo. So now, Luis Florit.
Well, I know Mateus since he began here at IMPA. He was my student in 2 or 3 courses. I don't remember.
2 courses.
2 courses.
Isometric
Okay, so it was a pleasure to know you, to interact with you, and to have you around. And about the thesis, I like it a lot, especially the relationship between the other local mathematician, because I consider Anna Ivaldo as a little bit local, even if they don't like it. I consider them a little bit local. So it's nice to see how the geometric analysis group interacts strongly among them. This is very nice. This is really nice. And about the thesis itself, I made several corrections that I gave to Mateus already, so I am not going to say anything else about that. But the only question I have is that there is always this square root of 3/8, right? That you got from the El Sufi work. And you told me, I think 2 months ago, that you have no other idea how to extend past that number.
Yeah.
Did you think about that or anymore, or you got stuck?
I think a little, but every day that I have, I don't how to proceed. I try use a kind of inverse function theorem for do this, but my first idea for construct this ace is using like an inverse function theorem. Prove there is a function of A dependent of R, but when I do this computation in pi over 2, is a singular point. The Jacobian is 0, so I can use the inverse function theorem here and forget the uniqueness here. The other ideas and try use every idea not working this. And this ODE setup is, I don't understand so better this Hamiltonian system. I just read the work and understand what they do and feel I can use this for get this estimate. But for uniqueness, I think is more difficult. You need do a very, very careful analysis of this Hamiltonian system. So I think I need I need to work with someone with the dynamical system that understand better this for get this.
Maybe it's false. Maybe it's a bifurcation point or something.
Yeah, other idea is using some continuation like methods, but I don't realize how to do this.
Okay, just a thank you.
Thank you.
Obrigado, Florit. Então, eu também vou fazer perguntas. Obrigado, Mateus, pela apresentação. Gostei muito, ela evoluiu bastante. A de hoje foi realmente excelente. Bom, os meus comentários eu também já passei para você, a gente discutiu extensivamente, né? E talvez uma curiosidade, né? Eu fiquei pensando, agora que você tem essa observação sobre o índice, né? Se você saberia dizer que uma faixa de Möbius, mínima free boundary em B4, com o índice 5, se ela é imersa por primeiras autofunções. E aí, sendo imersa por autofunções, de repente ela é a sua. Essa é a minha pergunta, né? Então, você saberia concluir isso, do índice 5, concluir que ela é imersa por primeiras autofunções?
If the index is 5, we have this relation.
Sorry, just one second. Did you speak in English? I forgot.
Yeah.
And I forgot. Sorry, Misha, sorry. I started speaking Portuguese, so. Please. So, sorry. The question I asked Mateus was the following. So, if he knew if it's possible to prove that if you have a free boundary minimal Möbius band in B4, with index 5, then it's a must by first eigenfunctions. That's the question. Because in case it's true, right? So potentially he found exactly that Möbius band, right? So a classification by the index.
I think for lead with this question, we can try use this formula that relation the index and with the spectral index. We know there is a formula obtained by Misha and after that by Medvedev in this setup that related the index and the spectral index. And the spectral index is the number of the eigenvalues, in this case less than cotangent of R. We have the following, we have the n times spectral index minus the Morse index is n spectral index plus the moduli space here is 1 and here is 4. If the index is 5, we know that the spectral index is 1. Is 1, so they should be measured by first eigenfunctions.
Okay. So
It's not another option for spectral index.
You have the converse as well, right?
There is an upper and a lower bound.
Okay. Okay, so that was all I want to ask. Thank you, Mateus. Is there anybody in the audience who wants to ask a question? No? Misha? No? Okay. Okay, so I think now it's time for us to deliberate. I would ask Okay, so the committee has deliberated, and my pleasure to announce that Mateus' thesis was approved. Congratulations, Mateus.
Obrigado.
So I don't know if so if anybody wants to say something, you can say now, the committee, or otherwise I will say a few words.
I just say congratulations on nice work and hope to see more from you in the future.
Oh, thanks.
Ok, parabéns, Mateus. Muito sucesso aí
Obrigado.
na tua carreira.
Yeah. Congratulations, Mateus. I'm really looking forward for your next results. I think you contribute a lot.
Very good. E, bom, eu quero dizer especialmente que foi realmente um prazer orientar o Mateus nesses 4 anos. Foi muito interessante observar a evolução dele, que chegou aqui um sujeito bem tímido, mal olhava pra gente, e que agora está aí confiante, viajando o mundo, apresentando os resultados dele. É realmente muito, muito bonito de ver. E o trabalho dele eu achei realmente excelente. Ele escolheu um assunto difícil, porque é um assunto que está bastante em voga, muita gente pensando no assunto, e eu até no início fiquei um pouco preocupado, mas ele foi insistente, encontrou o seu problema e resolveu o seu problema, e isso foi realmente uma satisfação de ver. Então, Mateus, boa sorte aí na sua próxima etapa, nessa carreira de matemático, e muito sucesso.
Obrigado.